And then what I would like to do is I would like to move on to the next presentation in this section, which is by Teodor. So Teodor, I hope you are in the call and can start sharing your camera.
I am here.
Excellent. That's how we like it.
Good.
And Teodor will be presenting about semi-supervised learning. I'm not quite sure if that's the right summary, but go ahead, Teodor.
You said that, so that's what I'm going to talk about.
I did, right?
Yes. Wait, now you can't see my screen, can you?
We cannot.
No.
We hope you can fix it.
Yes, I just didn't click the button here. Can you see it now?
Not yet. And if everyone could mute that is not presenting, so not you, Teodor, but others, that would be awesome. We have a little bit of background noise from some people.
Yeah, you cannot see it. Wait.
Is the share button not working?
No, wait, it should work. Now you see it. But you shouldn't see the results from the beginning.
Yes.
Now you can see there. Okay, good. Okay, hello, thank you. Yes, I'm going to talk about semi-supervised learning, as John said. So, as you know, in practice, supervised learning is the most common machine learning paradigm out there, but the problem with it is that it requires labels. So massive effort has to be spent on data labeling, because in the industry, data sets are often incomplete and or of bad quality. And labels need to be of sufficient quality, as the performance of a machine learning model is influenced by the quality of the training data. And you have different strategies that you can use to get labels, such as crowdsourcing, for example, but crowdsourcing might not be attractive to all people because the lack of, mostly because you have to share sensitive data with them. And they might have lack of people with in-depth understanding of the problem and no business to create labels. And in-house labeling can be half as expensive as crowdsourced labels and also provide higher quality. So as I said before, supervised learning is the most common learning paradigm out there, and it uses labeled data. And then we have unsupervised learning, like clustering algorithms and so on, that uses unlabeled training data. And then supervised learning is something in between supervised and unsupervised learning, as it uses both labeled and unlabeled data to do classification. So semi-supervised learning can be different things, but most important, I will only be talking about semi-supervised classification. So semi-supervised classification is an extension of supervised classification because it uses unlabeled data as well. And in general, we assume that there is much more of the unlabeled data than the labeled data. But there are also others, semi-supervised settings you can use, like constraints clustering, which is clustering algorithms, but they also use labeled data. And then we have also regression problems we can solve, and other stuff as well. And we can basically divide semi-supervised learning into two categories. First, it's inductive semi-supervised learning. So given a training sample of labeled and unlabeled data, we train a classifier that predicts labels for future data or incoming data. And then we have something called transductive semi-supervised learning. So then you have you're given a training sample of labeled and unlabeled data, and then you train a classifier only for the purpose to label the instances that you already have. So the unlabeled data, you will just want labels for unlabeled data, then you can use transductive semi-supervised learning. So they don't work, generally they don't work on new data. Okay. So before I go into the more deeper algorithms, there's the most trivial semi-supervised learning algorithm is called self-training. And those kind of algorithms just uses its own predictions to teach itself. So you first put in your labeled data and your unlabeled data, and then you train a supervised classifier on your labeled data, and then you predict some of the unlabeled instances, and then you remove those instances from the unlabeled data and put them into the training data, and then you retrain the model until you have labeled all the instances, which is can be quite tedious, as if you have a model that takes a long time, then it will take a long time to train this model. So it might not be the optimal thing to do. So this year we performed a systematic mapping study where we identified the most popular semi-supervised learning algorithms that are used in practice. And we found that the four most popular ones are called co-training and multi-view learning. And then we have mixture models and the expectation maximization algorithm, semi-supervised support vector machines, and then we have graph-based models. So I'm going to try to explain how these work without bringing in too much math. But basically, co-training and multi-view learning assumes that you can have, if you have your features, then you can view them in two different ways. So, for example, you can call them X1 and X2, and then you predict labels using both views. So you input a training set that is initially they're the same, but they're different. So L1 and L2 are initially they are the same set, and then we have this repetitive procedure where we train a view1 classifier on L1 and a view2 classifier on L2, and then we classify the remaining unlabeled data with both F1 and F2 separately, and then we add the F1's top K confidence prediction. So K is a parameter that you can choose from the beginning, and then you do the same with F2, and then you add F2's predictions to L2, F2's prediction to L1, and then you remove this from the unlabeled data, and then you do this until you have no unlabeled data left, basically. And you can also generalize this to n different classifiers, and that's why it's called, and then we call it multi-view. So co-training is only 2 views, multi-view is several views. And then we have mixture models and the expectation maximization algorithm, and that assumes that that the data comes from a mixture model, and so a mixture model, for those who don't know, is a weighted sum of normal density functions. And if you have a supervised setting, then it's easy to find these parameters. You just use maximum likelihood estimation, which is pretty straightforward. But if you have a semi-supervised case, then you have also unlabeled data, and this will make the problem much harder because mathematically speaking, the log likelihood function will be difficult to optimize, and then you have to use this expectation maximization algorithm. And then we have the support vector machine. So usually ordinary support vector machines, they classify instances by creating a decision boundary, and this decision boundary is again found by solving an optimization problem, which is easy in supervised learning, but as we have unlabeled instances, we need to impose another loss function on the unlabeled data. But semi-supervised support vector machines take care of this problem as well. And then we have graph-based models. So they create they take the data and they create a graph like this, and then they build this graph based on the unlabeled and labeled data. And most of these algorithms are actually inductive rather than transductive, so you can only label the unlabeled data you already have. You can't bring in new data and label that data. Okay, but these are actually the most common. These algorithms are actually the most common one, the graph-based ones. Okay, so in this mapping study we found several semi-supervised learning algorithms that were based on these 4, and we identified about 79 data sets based on 4 data types: image, sound, numerical, and text data sets. And we identify, I don't know how many it was, but it was 23 applications where semi-supervised learning is used, so it's quite popular. And yes, and then we did actually a simulation study where we compared different semi-supervised learning algorithms, or we wanted to assess the sustainability of semi-supervised learning data sets using something called, yes, this is what David talked about item response theory. So basically we wanted to find out what data sets are the best data sets to compare different graph-based semi-supervised learning algorithms and how we can compare them. So as David said a little bit, so item response theory is a family of statistical models that are used to evaluate how latent traits of students, the latent traits of students when they are evaluated by a set of items. For example, so you want to let's say you want to evaluate the students' intelligence, and then you want to know what exams questions should I put on the exam to best evaluate the intelligence of the students, right? So what we did is that we used item response theory to evaluate what datasets are best for evaluating graph-based semi-supervised learning. So we have two parameters we're interested in. We're A, which is called the discrimination parameter, and then we have the difficulty level of the datasets. So how easy or difficult are they? So in these simulations, we assumed that 10% of the entire datasets were labeled, and the rest of the 90% were unlabeled, and we choose different semi-supervised learning algorithms based on graph-based learning, and we had a total of 13 of those. And then we used item response theory on that, and we ran the data. We ran each simulation on each dataset 10 times using different seed to account for randomness. So when we ran these simulations, we logged the accuracy of each algorithm, so how well they performed on each dataset. So we used a total of 12 datasets based on image, text, and numerical dataset. So, okay, now I see I have made a mistake here. I listed okay, so for images we choose the MINS dataset, the C410, which I think most of you are familiar with. And then this fashion MINS you might not be familiar with, but it's like the MINS, but it's clothing. And this is digits, handwritten digits. And then we have news article, this is the fake news dataset, so classify whether a news article is fake or truthful. And then we have the 20 news datasets, which consist of 20 different articles or different categories that you want to classify. And then the numerical ones we used were, sorry, it was a problem here, wrong here. It was the Musk dataset, the wine dataset, the Irish dataset, and the German dataset. And so, okay, so we ran these simulations, and then we could estimate this discrimination parameter and the easiness level, or the distribution of these two. And what we can say was that the only datasets that were suitable for evaluating semi-supervised learning were the Reuters, assumed, and the Musk's datasets, and that you can see here, these three. So the key takeaway here is that diverse datasets give a good discrimination, reduces uncertainty, and hence it's easy to determine which algorithm is better. And according to our result, it doesn't matter what algorithm you choose, because our datasets are not very discriminative at all, as you can see here. They are almost zero. It's only these that are not zero. Yes. So yes, I think that was it. So in the future, we also wish to do more simulation studies to answer other research questions regarding datasets and algorithms. And we also have one case study with Saab upcoming as well to evaluate semi-supervised learning algorithms. And if you're interested in trying out some as well, we're happy to help. Yes, I think that's it.
Teodor?
Yes.
That also leaves us a few minutes for questions. I think that everyone understands what we're here trying to do, that in most cases in deep learning or in any form of machine learning, we need labeled data sets. And the work that Teodor is looking at is ways in which we can get away with data sets that are only partially labeled and still achieve good outcomes. So I think that that's the key behind the work that is currently ongoing in our research. And what we have noticed is that there is actually a lot of and not so constructive results. I mean, especially the data sets like that Teodor just showed, they simply do not provide good ways of evaluating these algorithms. Only 3 of the data sets that were used actually give some mechanisms for evaluating the data sets. So I think that was an interesting takeaway. What I was hoping to ask others is if there are any questions that people want to ask. Was this really completely clear? Jesper, very good. Go ahead, Jesper. And Teodor, maybe you can stop sharing your screen because then we can all see each other.
Of course.
Just a question, maybe I haven't fully understood this IRT formulation, but doesn't this whole thing assume that you have this linear relationship between what you're trying to predict and not predict? So in many cases, I would say there's a bigger difference between being 99.8% accurate on something and 99.3% in terms of the end task. I mean, sometimes that last 0.5% is what really makes or breaks your application. So with this approach, doesn't it kind of assume that the hardness or simplicity of the task is linear in some sense?
And since we're back to IRT, I'm also inviting David to join in the conversation. David, if you have a chance.
What is it that I'm not sure? What is it that you think is linear?
I mean, if you showed for instance, the graphs you showed with the hardness or easiness of the different data sets that you had, or the different tasks.
Mm-hmm.
So, I mean, most of them, like you showed, were very simple. So they tended to be on the highly accurate side of things, I guess. So low variance between models, etc.
Mm-hmm.
But if we take voice, for instance, as an example, a voice assistant, I mean, there's a big difference between voice assistants being, or rather, let's say speech to text. There's a big difference between being, let's say, 90% accurate and being 93% accurate.
Okay.
And that small difference is much bigger than, let's say, if you're doing something where you are 10% versus 13% accurate.
Mm-hmm.
So that's what I mean with this non-linearity, but poorly stated, I admit that.
Yes, because we had actually very high results for some of the algorithms.
Yeah.
They were almost all above 90%, and I think this is why they are so easy as well, because it's better if they all are not performing super good, then it's easier to know which one are difficult or not.
Yeah, but I think that's not what Jesper was talking about. The idea behind IRT, and I've invited David to step in, but I think he is away from the keyboard right now.
Yes.
Is that you ask questions that discriminate between different algorithms. So if you, and it comes out of education, you have a class of people.
Mm-hmm.
If you give everyone a test and everyone passes, it doesn't tell you anything about the relative ability of the kids in the class. If you give them a test and everyone fails, you're in the same ballpark, basically. So what you're trying to do is you're trying to develop a sequence of questions such that you can find the capability of the individual child by basically picking certain questions when they fail on the previous one and picking other questions when you fail on the next one. And what we're looking for is on the algorithms that we're working on, we're trying to figure out how can we evaluate them by picking the data set that maximizes our ability to discriminate between the different data sets. And I see where you're coming from, yes, but I mean, there are two sides here. One is the ability of the algorithm doesn't necessarily, or of different algorithms, isn't necessarily progressing along a linear scale. It can actually be very different. That's what I think Teodor is showing as well. The other part that you were mentioning is, well, I need very high accuracy, otherwise my algorithm, otherwise the solution doesn't deliver any value to the end user. And if that is the case, then you need to put your the place where you apply IRT not on the 90% or on the 93%, but you need to put it on the 98% and try to find ways in which you can stretch the ability of the different algorithms by in that range where you need the system to perform well. That's I think the mental model to think about it. Does that make sense?
Yeah, sure. I'm happy with that answer. Thank you.
Thank you. And then Ivica, we're in Aishwarya's time, so you're the last one who has a chance to ask a question.
Okay, then very fast. I think also what would be interesting and I think it would be very much interesting for the companies to provide their data, because the results would very much depend on the data also, which type of data sets, and that could be also of a high, I think, value for the companies if such algorithms can be used. So maybe that would be good to use this commercial data from the companies.
Yes, because these data sets are some of them are very simplistic and small.
Yeah. No, and second, after Teodor has been doing quite a bit of research in this area, mostly on publicly available data sets. We are now starting to work with some of the first companies. We hope to kick off a case study with SAP after the summer. Teodor has also been out at Ericsson, but we are absolutely interested in having additional companies collaborate in the research that Teodor is engaging on. And I would really like to recommend to everyone to get in touch with us if you feel that there is some interesting topics to explore here. Thank you very much for pointing that out, Ivica. I think that made a lot of sense. And with that, and 4 minutes behind schedule, I think we are switching presenter. Thank you very much, Teodor. And